Hi folks, so in this video we're going to talk about how we can use our elimination method of solving systems of equations to tackle a system that looks like this, which looks a little weird, but we'll actually see is really not that bad. So instead of having a typical linear function in standard form, we actually have an equation here that looks like 3 over x plus 6 over y equals 1. Now if it was in standard form and I had something like this, 3x plus 6y equals 1, that wouldn't be so bad, but now it looks kind of funky. So first off, we do know that these two graphs, they are not lines. They're nonlinear, for sure, right? Because we actually know that the domain and range, neither of them include 0, right? Because we would be dividing by 0 if that was the case. So they're not linear for sure. I don't actually know what the graphs look like, but that doesn't matter in terms of actually solving it algebraically. So graphing it, we could, again, you could graph it to find the solution by seeing where they intersect, but since I don't know what the graph looks like, that's kind of out the window. So let's solve it algebraically. What I'm going to do is I'm going to rewrite this equation into something that looks a little bit more familiar. So I'm going to rewrite this one as, instead of 3 over x, I'm going to write it as 3 times 1 over x plus 6 times 1 over y equals 1. And then we'll have 3 times 1 over x plus 7 times 1 over y equals 1. Sorry about that. Okay, so big deal. Why did I do that? Well, here's the reasoning behind this is because if I had something like this, and if we kind of blur our vision a little bit, then this is really, I could just call this, I'm just going to call it another letter. I'm going to call it A. And I can call this B. So what I'm effectively doing is substituting A and B here. So really what we're doing is making a substitution where we will say, let A equal 1 over x and B equal 1 over y. So now our system looks like this. 3a plus 6b equals 1. And then I have 3a plus 7b equals 1. This is an equation a system that we could solve because 2 equations, 2 unknowns. Let's just go for it. So depending on how you want to go about it, you could just subtract these 2 equations right now, or you can flip one to make it negative and then add them. But I'm just going to subtract them because just like how we can add the same number to both sides, we can subtract from both sides. So let's see, 3a minus 3a, that'd be just 0. So now we can see we eliminated one of our variables. Let's see, 6 minus 7, so that'd be negative 1b. And then 1 minus 1 would just give me 0. Oh, sorry, not 1, it should be 2. I thought that looked weird. This should be 2 here. Oh, no, not there, here. Okay, so now I have 1 minus 2, which is negative 1. And that tells us that b is equal to positive 1. Okay. Actually, I'm not going to box that because remember, we're not looking for a and b. We're looking for x and y. So hang on to that just for now. Because now we need to figure out what a is. And so I could just take this b and plug it into one of the equations. So I'll plug it into the first one, I guess. 3a plus 6 times 1 equals 1. Oops. That'll give me 3a equals, that's going to be negative 5. And then the last part, just divide by 3. So a equals negative 5/3. Okay, but remember, b is 1, but b is actually 1 over y. And a, which is negative 5/3, is actually 1 over x. And so actually, to solve this would mean that y equals, well, not 1, but the reciprocal of 1, so it'd be 1. And then x would equal negative 3 over 5. Last thing we could do is, again, check the graph. So what I did is I just took those equations and threw them into Desmos here, right here. And we could see where they cross, and that would be the solution. So it's hard to see here because they're so close together. But if I plop in our points, so I believe it was negative 1, comma 5/3. Sorry, I had it backwards. forgot. Negative 5 over 3, comma 1. Wait, 3/5. Sorry, I'm all backwards. Negative 3/5, comma 1. We can see that that is actually where they cross. And of course, it's a little hard to see because we're so zoomed out. But if I really zoom in, really zoom in, you can definitely see that's where they cross. Now, it does look like they intersect again down here at 0. And Desmos will not let me trace the graph here, unfortunately. But it kind of looks like it. But actually, and you kind of see it as I'm zooming in, and the reason it's getting filled in is because you could plug in closer and closer values to the origin. But remember, 0, 0 is not, we can't, 0 is not in the domain or the range of either of these ones, because you can't plug in 0 for x and you won't get 0 for y out here, right? Because that would involve that you divide by 0. So actually, as much as it looks like they cross at 0, 0, 0, 0 is not actually on either graph, right? So that's how we can use what we know about our elimination method to solve things like this, which maybe don't look super obvious, but with a little bit of tricky substitution are definitely solvable. All right, see you in the next video.